This is 2009 AP Physics B FRQ question. Again, I have a link for this problem online, underneath the video. So please try to solve the problem before you see the solution that I will give you. And also after you listen to my solution, still go and see how the points were assigned. Two small objects labeled 1 and 2 in the diagram above are suspended in equilibrium from the string of length L. Each object has a mass m and charge q. So let's underline what is given. The charge of each object is positive q, the mass is m, and the length is given. Assume that the string have neglectable mass and are insulating and electricity neutral. Express all algebraic answers in terms of the information that is given, which is L, little q, probably the little q, another charge is going to be appearing somewhere there, and the big Q, and fundamental constants. On the following diagram, sketch lines to illustrate a two-dimensional view of the net electric field due to the two objects in the region enclosed by the dashed lines. So I have to show electric field lines coming from two positively charged spheres. So if they're positively charged spheres, the lines are coming from the positive charge out of the charge. So it's going to be something like this, maybe like this, like this. And because they are exactly the same charge, I have to follow the same pattern to show that they have the same strength. So, and then I have to show that electric field lines are coming out of the positive charge. And I see one line that does not match the other side, so I'm going to redo it. Because they have to match both sides. So if you want to add another line on this side, you have to add another line on that side. If you want to add this one right here, you have to add another one on this side to show that they are exactly the same. So that was for part A. For part B, derive an expression for the electric potential at point A. So I need electric potential at point A. And electric potential is voltage, potential difference. When they say electric potential, they mean electric potential difference, and potential difference is the voltage. So the definition of voltage is work done per charged mole. So how much joules needed to move 1 coulomb of charge. So, and that is the voltage. So when they ask me potential difference, they mean potential difference in energy in order to move the charge. So shown in the diagram at the top of the page, which is midway between the charged objects. So I have to derive the expression for electric potential at point A. So let's look at the point A. So here is the point A. And I have to determine the electric potential at point A. And again, the electric potential, I'm going to derive the formula here. The definition is the work per charge. Also, the work is equal to the force acting on the object times the distance over the charge, and force over the charge is electric field times the distance. So you could use any of these formulas to calculate the potential difference that is caused by the charge. Also, another good formula to know, I'm going to put this one over here and work it out on the other side. The voltage is equal to the force, and it's electric field force. So electric field force times the distance over the charge. And this charge is a test charge. So the Q at the bottom is the test charge that plays into electric field. So if that could be the point A, which in our case, we do not know the charge of point A. So the force F is electric field force. So I can rewrite the formula of electric field force is Q1, Q2 over the distance squared times the distance and divided by the Q. And so if I look at this as if it was the source was charge 2, then the 2 and the 2 would go away, and the distance and the distance would cancel. So I could also use the formula Q1 over Q2, and Q2 can be cancelled, over the distance. So I like to say test charge. When I explain this to the students, I like to say that it's the test charge at the bottom of the formula. And I also like to say, instead of 1, the source of the electric field lines. So you also could use this formula. So going back to the problem that they gave us, let's look. They asked me to find the potential difference at point A. So if I want to find the potential difference, I could use this formula, the one that I just found, this formula, and point A, imagine electric field lines like a water in the fountain. So if you have the water coming out of the fountain, and so there is water everywhere, and if you take your finger and you place the finger somewhere near the fountain, so here's your hand, and you place your finger near the fountain, you will feel a lot of lines, like current floating around your finger. But the farther you take your finger and place into the water, the less electric field lines, we're going to look them like the stream is going to be coming through your finger. So I look at it, the problem with electric field lines exactly the same. So at point A, there are electric potential difference between point 1 and A, or charge 1 and A, and there is potential difference of charge 2 and A. So there is like double potential difference between the charges. So if I want to calculate my potential difference, I have to double and the charge is the same for both of them, the potential difference between one point and the other. So let me find the space right here where I can write this. I'm going to use the space above. So for B part, I can say that my voltage is equal to, at point A, is equal twice the potential difference between 1 point. So that could be K, Q, and over the distance. So I'm using the formula that I just derived, this one on the left, on the top left. And the distance, when I talk about the distance, it's this distance. And this distance is L sine theta. So I'm going to come back and I'm going to rewrite it as 2K Q over L sine theta. And that would be my answer for B. For C part, on the following diagram of object 1, draw and label vectors to represent the forces on the object. So the forces acting on 1 are the tension force. Then you have mg, the gravitational force, and electric field force, pushing it away from the other positive charge. We don't ever draw the components of the force vectors. So if they ask you ever on AP exam to draw the forces, at first always make sure that your forces are connected to the dot they give you that represents the object. So make sure that all of them always connected, and don't show the components. So don't show the x and y components of the vector force. They only ask you the forces, not the vectors, not the components, not the not the vector components, and not the acceleration. So for D part, using the conditions in equilibrium, write but do not solve two equations that could together be solved for Q and the tension T in the left hand string. So I'm going to rewrite my forces and then the equations. So I have the charge Q and the forces acting on the charge tension mg, and electric field force. Then the tension has horizontal component and the vertical component. And in the formula, this is your theta, correct? So I have this angle theta. Then if I look at my graph, this is my theta. So that means this is T cosine theta, and this one is T sine theta. So two x and y equations that I can write in this case are, for the vertical, for y-axis, I have T, let's do x, the x-axis first. T sine theta minus Fe, electric field force, equals to 0. T cosine on y minus mg is also equal to 0. There is no acceleration. So it's the net force is equal to ma, but there is no acceleration. Then if I divide one side by the other, and let me explain. Oh, wait, let me do this first before we do the division. I do not want to erase it right now. So let's rewrite it this way. I have T sine theta equals to Fe, and that is Q times Q, which is Q squared, over R, or over the distance between them. And that's the distance between the two charges. So that's the distance. And I have T cosine theta and equals to mg. Oh, and just to go back right here, your distance is equal to 2 times L sine theta. And let me go back so you can see why it is 2 times L sine theta. Do you remember we showed that this part is L sine theta? Well, this is the distance. This whole thing is the distance. So it's 2 times L sine theta. so going back to our problem. So now I can do what I wanted to show you a little bit earlier. Like, I'm going to divide the left side and the right side, and this is how I can do this. You know that 4 times 5 is 20, and 4 times 4 is 16. I can use this same trick that I'm doing right now. I can divide one side by the other, and I can say 4 times 5 over 4 times 4 is equal the same as 20 over 16. So I can use this trick sometimes to solve system of equations and eliminate some of the unknown variables. In our case, it's the t. So t and t can go, and what I get is sine over cosine. I'm going to keep it for now as sine over cosine. I'm not going to write tangent yet. Is equal to fe, and fe is equal to kq squared over d. So that's q squared. Instead of the d, I'm going to write 2l sine theta. And still on the bottom, I have mg. So my final equation is equal to, I have to solve for q. Well, they ask you not to solve for q. So you could write tangent. You could write tangent. Theta is equal to q squared over 2l sine theta mg. Because they didn't ask you to solve the equation, you can leave the equation as it is. And in this equation, k is a constant, l is given, theta is given, mg is given. So you could solve for your charge. And k is a Coulomb's constant, 9 10 to the negative 9.